This talk is about unsupervised learning. And I'm going to start this talk by a brief introduction in which I will try to motivate why is unsupervised learning needed. And I hope that at the end of the introduction, you'll all be convinced that it's a good idea to work on these kind of models. So nowadays, we see a lot of amazing applications of machine learning. For instance, in state-of-the-art computer vision models, nowadays can run on mobile devices, detect people, find the posture, and do that in real time on mobile devices, so on pretty small hardware. And I think these recent advances in machine learning and computer vision are really amazing. However, they are always based on supervised learning. So in order to train models that are capable of solving such problems, you need couples of X and Y, so X the data and Y the labels. And you're going to train a function, a predictive function F, which is going to map from images to this label space. And in order to train these functions, you usually need a large training set. So these data points, you have n of them, and n can be pretty large. Moreover, the label space need not be just classification sets. It can be like a structured, complicated set. And this makes the annotation even more complicated. So great advances, but they are fueled by manual annotation. So I'm going to walk through 3 examples. Let's say that you want to do binary classification, cat classification. Is this image a cat or not? So you look at the image, it's a cat. So you set the label to 1. And basically annotating images is going to be pretty fast, just saying yes or no, is the object in the image. However, now if you work with object detection, the label set is going to be a set of 4 numbers which describe the size of the bounding box for the object. Again, if you take this image, you need to define the rectangle which contains the cat. So this is already much more complicated than just saying yes or no, is there a cat in the image? And it's more time consuming too. If we now move to object segmentation, the label set is the set of binary images, which are going to be 1 where the object is and 0 otherwise. And in the case of this image, you would need to provide a complex shape that contains the cat. So this is even more complicated. Now, if the object is really highly deformable, if the object has heavy occlusions, we don't see a lot of parts, or if the image is complicated and cluttered, it has a lot of elements, the annotator is just going to be like, I don't want to do this. And he may even provide pretty bad bounding, boxes like this thing. So why do I talk about this and why I really feel strong about this stuff is because I did my PhD on action recognition in videos. So in human action recognition in videos, you're provided a short video clip and you're supposed to say what action is performed inside. So here are 3 examples from the Hollywood 2 dataset with labels sit down, and stand up. So the label set is usually a set of actions defined by hand: sit down, stand up, open door, eat, hug, kiss, run, fight. And the definition of these actions is very ambiguous. It's just a researcher who thought the human actions are these ones, but I'm not sure that this is the perfect vocabulary. And so annotating human actions is a horrible pain. The manual annotation of an action means that basically you need to scroll in time and say, here the action begins and here it ends. So there are some tools to do that. These are pretty old slides, so it's from 2013, 14, I think. There may be new tools since then. But the UI of these tools is pretty bad. And the definition of the action is very imprecise. When does an action begin? When does it end? Setting aside the fact that it has a definition at all, like setting a beginning and an end is very complicated. So I'm going to show you a short video clip, which is labeled, a human labeled as eating. And if you watch it, like all this is supposed to be eating. But maybe, like for me, maybe eating just starts when the plate is on the table. Or is it when he actually grabs the burger? Or is it right now? I mean, that's really imprecise. Like there is no good definition for that. And I learned how hard it is the hard way, because my supervisors, so Ivan Laptev and Cordelia Schmidt, designed this Hollywood 2 dataset in 2009, where you had roughly 1,600 video clips taken from, with 12 actions, taken from 70 Hollywood movies. So at some point they thought, hey, let's make Hollywood 3. And Hollywood 3 would be basically taking all these 69 movies and annotating them exhaustively with all occurrences of the 12 actions. What it means is that you need to watch 69 movies and find every time someone is opening a door. So the annotator who was supposed to do that refused to annotate some of the movies. For instance, Crash by David Cronenberg. I don't know if you have seen this movie. It's pretty drastic. So the annotator refused, and I had to do it. So I watched this movie like 5 or 6 times, looking for opening doors, looking for eating, sitting down, and standing up. Trust me, you don't want to do that. So we thought that we want to work on stuff which is weakly supervised. Come up with information sources that are noisy, but we are going to tell you something about what's happening in the video. We were inspired by work on images, where researchers have proposed methods for identifying people in images, not based on human labels, but based on captions in news. So you get a lot of information from this kind of captions, but it's very imprecise. So people who are in the picture can be never mentioned in the caption, and some people who are mentioned in the caption don't appear in the image. Yet, if you take a lot of such images and come up with a robust method, you can come up with the right labels at the end. In our case, we wanted to work with movies, so we decided to look at movie scripts. So movie scripts are pieces of text like that, meant for shooting the movie, and they are composed of 3 elements. Scene anchors. Do you see the red thing here? Okay, scene anchors, describing the setting, which basically says where the scene is taking place, and it's the beginning of a new scene. Scene descriptions, which are gonna describe what's going on. So an officer blows his whistle several times. There is a pandemonium as native guards begin to round up people, etc. So it's describing what's gonna happen on screen. And there are monologues, which give you what people say. Basically what actors are gonna pronounce. The problem with this data is that it's not temporally aligned. You don't know when in the movie or in the AVI file or MKV file it's happening. You don't have a temporal alignment. So a method proposed in 2008 suggested to align the movie scripts with subtitles, because both contain speech. So subtitles, you can align them with monologues from the script. And given that subtitles, like people use subtitles to watch movies on their computer, and they have temporal positions. So by just aligning the subtitle file with the script, you get a rough idea of where the scene description should be happening in time. So to give you an example, this is actually taken from the script. It's describing a scene in Casablanca. As the head waiter takes them to a table, they pass by the piano, and the woman looks at Sam. Sam, with a conscious effort, keeps his eyes on the keyboard as they go past. The head waiter sits Ilza. Let's watch the video clip that is aligned to this thing. So indeed, there is like the head waiter. They pass by the piano. The woman looked at Sam. I guess that this is Sam. And actually, that's where she looks at him. He's going to look at the keyboard with a conscious effort. So that's right now. This guy isn't mentioned. And then the head waiter sits Ilza. So well, that describes it pretty well. And most things that are described here really happened in the video. However, it's not like a symbolic representation. You cannot do like machine learning with something like that as a label set. So in my PhD, I had two contributions. The first one was working with faces and actions and saying that basically in the script, there is always someone doing something, and we identify subjects and verbs in the script and do a joint optimization of person recognition and action recognition. So these are like qualitative results from this paper. It's from 2013. It's not that great, but you're gonna get the gist of it. So basically it was predicting like Ilza is other, Rick is gonna be walking. Then Rick is sitting down. It's a false prediction for the other track. But basically that was the idea, kind of come up with a way to extract information from the movie script and generate some kind of labels to train a model with that. So the second contribution was about temporal alignment. As I mentioned before, annotating videos is really, really tough. You don't want to do that. So we want to exploit the fact that things happen in order. So first, there's going to be this officer. Then there's going to be two policemen stopping a white civilian. And after that, there's going to be someone patting his pockets. Basically, we came up with a model where instead of annotating a video by precisely saying from frame 24,542 to something, someone is going to be opening a door. You're going to just watch a scene and say, like, first there's going to be someone opening a door, then standing up, then shaking hands, or standing up, shaking hands, and opening a door. And if you have enough such data, you can come up with a model which is going to learn a model for these actions and at the same time align the labels in time. So here are some qualitative results. Basically, each clip has only received as information the order in which the actions are going to appear. On the right, you have the action vocabulary. The GT is the ground truth that was annotated by a human. So someone really saying, like, from here to here, there's going to be this action. And below is our prediction. So the video is slowing down, and there's going to be the name of the action in green if it's correct. And in most cases, actually, it was correct. An interesting thing is that our model was biased towards very short and most discriminative parts of the video. So it wasn't choosing these big parts of video, but only what's most typical for the action. And I mean, here you're going to see with the green bar, which is supposed to be eating or drinking, that again, this eating action is very illy defined, and that our method managed to find a piece which for me is like undoubtedly about drinking, like, because this is labeled as drinking. It's like pouring for me, it's not drinking, but yeah. So all this stuff that I described up to now was pre-deep learning. So in this video recognition work, we were using handcrafted features. Dense trajectories, histograms of oriented gradients, and the data was only there to train a linear model on top of handcrafted features. However, today, you need data to also train your features, because you usually use some kind of convolutional neural network, multi-layer perceptron, LSTMs, something like that. And unless you take a pre-trained network on ImageNet, you need more data to also train your features. So in this talk, I'm going to talk about two things. First is what kind of unsupervised learning can we do for natural language processing? And how can we train word vectors for many languages in a way that would be efficient? And I'm going to present two papers. The first one is enriching word vectors with subword information that we submitted to a journal, Tackle, in 2017. Another one about learning word vectors on more data for more languages and how to get high-quality data to train these word vectors, which we submitted to LREC, which is a dataset conference. In the second part, I'm going to talk about unsupervised learning for computer vision and how to train CNNs without any labels. And this is going to be basically a mix of two papers. The first one, Unsupervised Learning by Predicting Noise, which we submitted to ACML, and Deep Clustering for Unsupervised Learning of Visual Features that we recently presented at ECCV. So all this work, I haven't done it myself. I've done it with, what's going on here? I've done it with amazing collaborators at Facebook. It's my collaborators that makes it bug. With Edouard Grave, Thomas Mikolov, Armand Joulin, Matthijs Doos, and Mathilde Caron. And I'm going to start with unsupervised learning for natural language processing. Is there something like... What's going on out there? That was the right thing to do. So, let me start this part by talking about language modeling. So, language modeling is a problem where given a sequence of tokens, x1 to xt, with each xt being in the set 1 to k, so k is, for instance, the number of words, and x1 to xt is going to be a sequence, let's say, a Wikipedia article. The goal of language modeling is computing the probability of a sequence, the probability of seeing this particular sequence of tokens. And how do you do that? You start by factorizing the probability as taking the conditionals every time conditioning on the past. And then the goal is basically modeling the probability of the token at time t, given all the tokens up to time t minus 1. And this problem is very natural is a very natural unsupervised problem for language for NLP. And it's a great unsupervised task because you have real targets which are in a discrete set 1 to k, and you have something to predict given some context. So it's like unsupervised learning based on supervised learning techniques. So standard language modeling models include, for instance, n-gram models, which are very simple, where you basically compute the joint probability of observing a token at time t and t minus 1, and you divide that by the count of the token at time t minus 1. And there are some interesting extensions to this very simple model, which is not always well defined. Another alternative is log linear models, basically linear models of some handcrafted features of the past. So you need to come up with a feature of the past, which can be a bag of word, for instance. So you compute a bag of word up to time t minus 1, and then compute the probability as a softmax of a linear function of these features. And of course, nowadays, you get all the huge literature about neural network-based language modeling with architectures such as the recurrent neural network, gated recurrent units, LSTMs, and more recently, transformers, which allow you to compute a more complicated function of the past. So what are these models useful for? They are useful when you need to generate a sequence. So there are many applications that require that, and you either do that by generating according to your model. So basically, you take the argmax of your probability over the tokens given the past, and you do that greedily at each time step. You can do some kind of beam search if you want to be more fancy. Or you can also use it to rank some candidates that you would generate with a heuristic, and that would allow you to score one of the candidates based on the fact that it's more likely to appear. So this is used in many applications, and the first one I think about is speech recognition. So every time you have a device which recognizes speech, you need a model that is going to basically transform the utterances into some kind of symbols and then make sure that the sequence of symbols is kind of likely. You're not saying total gibberish. Other applications which are related is machine translation. So when you translate from Polish to French, Polish to English, you're going to have a language model on the decoder side, which is going to basically rank the translation based on how likely they are to be actual good French. And other applications you can think about is, for instance, image captioning, where you generate a short text description given an image, or text summarization, and I guess there are many other applications you can think about. Most recently, it has been shown that actually training very large, big models on a lot of data gives you very good features to do stuff with documents. So basically training a language model, if you take the hidden states of the language model, there are good features for linguistic tasks. There is an interesting sub-part of language modeling, which is about modeling language on the level of characters, not on the level of words, but predicting each character one after the other. And it's motivated by the fact that some languages have very large vocabularies. So if you have a very large vocabulary, you need a classifier which is going to classify in an output space which is potentially very large. If you take a small subset of EuroParl, very quickly, so EuroParl is a machine translation dataset in which you have like the proceedings of the European Parliament, so you have aligned data for many languages. If you take a subset of it in Finnish, very quickly you're going to have a vocabulary which is more than 200,000 words, different words, because Finnish is an agglutinative and agglutinative language with high morphology. It's basically like there's so many forms that the vocabulary is going to explode. So maybe for such languages, such as Finnish, Turkish, it's actually better to work on smaller units. So syllables, characters. Most recently, people have been working a lot with BPE, byte pair encodings, and this is a good example of smaller units you can think about. I myself, with some colleagues, have proposed a model that was a hybrid word and character level language model, which was basically exploiting both cheap word level language modeling with some more expensive character level language modeling in order to allow you to predict even for words that you've never seen in the training set for languages such as Finnish. So after this brief introduction about general unsupervised learning for NLP, I'm going to describe our paper, Enriching Word Vectors with Subword Information, which was joint work with Edouard Grave, Armand Joulin, and Tomasz Mikolov. And you're going to see why it's related to language modeling in a few slides. So the idea of representing words as vectors has been out there for quite some time, and it's based on the idea of the distributional hypothesis. Basically, in 54, can I just plug? Oh, no, I cannot. I hope I have enough battery. Okay, sorry. So basically, words that are used and occur in a similar context must share meaning. So every time a word is used with the same neighbors, it should be meaning the same thing. And there were some propositions for computing word vectors based on this idea already in the 90s. Based basically on the co-occurrence statistics, so you compute a count for each word, how often does it appear next to another word, and you can factorize this count matrix by doing an SVD or something else, and you obtain some kind of word vectors. Then this idea was applied more recently by the work of Kolober and Weston, Mikolov et al. With Word2Vec, or Pennington et al., which is glove. These are basically like the most widely used word vectors that people have been using, like practitioners in NLP have been using. So I'm going to describe now two variants of the models that were proposed by Tomasz Mikolov. And the first one was the skipgram model. In skipgram, if you have a sequence of tokens such as this one, the mighty knight Lancelot fought bravely, and the current word is W is knight, The goal of the skipgram model is, given this word, predict every word in the context. So you have like 5 independent predictions here, and this looks a bit like language modeling, and that's why I was saying that there is a link between the two. But it's not about like predicting the next word given the past, it's about predicting the context given one word. So in this model, you model the probability of a context given a word. So you define a feature for word W, we're gonna call it XW. You define a classifier for the context word C, and you call it VC. And you say that the probability of the context word given the word is gonna be the softmax of the dot product between the feature and the classifier. And once you've trained this model on your data, the word vectors are basically gonna be the features that you had in your model. Now, there is a second version that was proposed in Word2Vec, and it's called the SIBO model. In SIBO, given the same sequence, the goal is to predict the central word given all the context. So this time, you only predict one token given the context. So this looks even closer to language modeling, except from the fact that you see the future in order to model your probability. So in this case, you model the probability of a word given a context. So you define some kind of feature for the context. We're going to call it HC. A classifier for word W. Again, you're going to compute the probability of the word given the context as the softmax of the dot product. And it's called SIBO because it's continuous bag of words. And the feature for the context is just the sum of the representations of each word in the context. So both these models have some drawbacks. First, it's not a proper sentence representation, but I'm not really gonna go into more details about that. The most important part for me is that it's not actually exploiting morphology. So words which share characters inside, share some radicals, they don't share parameters. So for instance, if you have 2 words in English, disastrous, disaster, they're gonna be just encoded as independent vectors in the embedding table, and they're gonna have a separate entry in the parameters, this one and this one. The same goes with like a French conjunction or any kind of grammatical variation. However, these 2 models were very simple, very fast to train, and therefore widely used because it was very easy to retrain Word2Vec on your data and obtain very good quality word vectors on your data. So in our work, we wanted to exploit subword information and making sure that grammatical variations of the same word are still gonna share, like it's based on the observation that grammatical variations still share most of the characters in the string. I guess we as Poles know it very well because we have declension in Polish with 7 different cases in singular and plural. So uniwersytet is gonna appear 14 times with like less than 14 different spellings. But in a Word2Vec model, each of these strings would have a different set of parameters. And the second thing is that compound nouns and agglutinative languages could benefit from that. For instance, German, if you have Tisch, which means table, and tennis, which is tennis, Tischtennis is playing tennis on the table, so basically ping pong. And you want kind of this word, this thing to have parameters which are shared with these 2 because you don't want to learn everything from scratch. So we basically want to exploit morphology and use the character sequence within a word to represent the word. So how do we do that? We represent words using character n-grams. So if you have a word such as ananasek, you're going to represent it using all the trigrams, all the 4 grams, all the 4 grams, and all the 5 grams, 6 grams, sorry. and you're going to take the sum of all that. We add some special positional characters at the beginning and at the end, so that there's a special meaning to the prefix and to the suffix of a word. So for instance, it's going to be like special character univers and a sequence of the characters and the end symbol, which are going to allow you to share also these grammatical inflections between different words in the vocabulary. So what is our model? We do exactly as in skipgram, so the model in which, given a word, you predict context words. We're going to define a feature for word W, HW, and a classifier for word C in the context, VC. And exactly as before, we compute the probability of the context given the word as the softmax of the dot product. And this time, the feature for the word W, it's not XW, it's HW. And we say that it's the sum over character n-grams, and we have a representation for each character n-gram. So for the word mangerai in French, you're going to have a vector for the word itself plus one vector for each substring in your word. So there are some important details in this model. The first one is that you cannot build a dictionary for n-grams. If you have 1 gram, so different characters, let's say you work with UTF-8, you're going to end up with a few hundreds of different symbols. If you take into account all the pairs of UTF-8 characters, you're going to have like a large amount of entries. So we don't want to go further, and we do hashing. So we use a hashed dictionary, and in order to hash from a sequence of characters to an entry from 1 to B, we use the Fowler null-vo hash, which is just one of the hashing strategies on strings. And there is a trade-off here, because you need to find a trade-off between choosing B large enough so that there's not much collisions in this hash table, and at the same time that you don't explode memory. In the end, in practice, we use B roughly 2 millions. There are collisions, and these collisions actually don't hurt performance that much. The second important detail is approximations to the loss. So we replace the multi-class multinomial logistic loss by a set of binary logistic losses. So if you assume that your label is in -1 + 1 to the power k, so it's -1 for all the words that it isn't, and 1 + 1 for the one you're interested in. The multinomial logistic regression reads something like the negative log likelihood of it reads something like this, and we basically replace that by k independent binary classifications, which in itself doesn't make your model more efficient, because like what's hard in this is computing this part, which is the sum over k, and in that case you still have this sum, and what we do, and this k is basically prohibitive, it's very large, it's 10 to the power 6, 10 to the power 7, so we use negative sampling, and in this thing there are only a few terms, there's one term which is a positive, and out of the negatives we subsample them, we just take a few of them, 5, 10, 15, and the other ones are left aside. So the great thing about this model is that it's able to produce word vectors even if you have never seen the word before. So since we define the feature for a word as the sum over the character n-grams of the vector for this character n-gram, and that's how we do on the training set, if there are some words that you've never seen because there's a different inflection or it's a name of a molecule which you've never seen before, but it looks a bit like what you had before, you won't get the word vector itself, but you still get this thing. So this is very useful in application where you have very large vocabulary, or misspellings, for instance, because like if you train on Wikipedia, Wikipedia is roughly well spelled. People write correct English and French and Polish on Wikipedia. But if you try to use it on the web, well, on the web people don't write as well as we on Wikipedia. So sometimes you won't have a vector for the spelling that the person actually wrote, But since you do the sum over character n-grams, you're going to be able to make a Franken vector out of it. The other thing, which is related, and it's, I guess, just the dual of this thing, is that it allows you to train word vectors on much smaller data set more efficiently. So this model, we evaluated it in 2 ways, which are intrinsic evaluations. The first one is word similarity. So given pairs of words, you show pairs of words to people, and these people give you a judgment of similarity. You do that 10 times for 10 different judges. And here I just give you a few examples. Someone like, on average, people said that yodeling and singing is related to 7.5 out on a scale of 10. That inducement and motivation is 6.29. Premises and premise is 6.83. Winners and walloper is 1.67. Okay, so this is just a data set that people build that reflects the similarity between 2 words. And given word vectors that we train with our method, we can compute a score between 2 words as the cosine between the 2 vectors, and then take the Spearman's correlation between the scores that we produce with our vectors and what humans said. So we did that for Arabic, German, English, Spanish, French, Romanian, Russian. So these are the data sets that we found of this type. And we compare to skipgram, SIBO, which are word2vec, and our model. What we see is that our model works best on data sets which contain hard words such as rare words in English, where the improvement was of 4%, or for languages such as Russian, and we don't have Czech is in the next thing. So yeah, it works well for morphologically rich languages, and especially when you have rare words in your dataset. I see I have a typo in my thing. It should appear later, this thing, sorry. So given triplets of words, there's another evaluation called word analogies, where given 3 words, so Paris, France, Warsaw, you're supposed to predict the analogy. And here, of course, it's going to be Poland. And you predict the analogy by taking your vectors and computing the word vector for France minus the one for Paris plus the one plus Warsaw. And you do a nearest neighbor query on your data set. And if it's Poland, it's +1, otherwise it's 0. So you evaluate this thing using accuracy. And we did that with the data sets that we found back then, which was for Czech, German, English, and Italian. And these categories of analogies are divided between semantic and syntactic, semantic being more on the meaning and syntactic more about the grammar. What we see is that our method works really much better on syntactic analogies and doesn't degrade much the performance on the semantic analogies. So we also did a comparison with state-of-the-art character-aware word embeddings. And they are separated here because they use different training data, so we want it to be comparable. We train exactly on the same data as them. And what we show is that we managed to outperform all previous methods by a significant margin. So the thing that people in the NLP community say is that these intrinsic evaluations based on word similarity, word analogy don't mean anything. They're useless, and you should evaluate on downstream tasks, on tasks you're really interested in which you're going to use your word vectors. So we trained a language model, an LSTM language model, on Czech, German, Spanish, French, and Russian by initializing the lookup table in the language model with our vectors, and we compare with some state-of-the-art character-aware language models. What we show is that actually, we beat them with a simple LSTM for most of them. And that if you update the word vectors with skipgram, you can do even better. And if you use the FastText word vectors, well, you do even better. So the last quantitative evaluation that I wanted to show was that we trained word vectors with increasing the amount of data that we use to train them. So basically 100% means that we take the full Wikipedia, and 20% we just take the first 20% of the Wikipedia dataset. And we evaluate with word similarity on the German dataset and on the rare word dataset. What it kind of shows is that you can get very good word vectors with very small data using our method as compared to SIBO, which had to use a lot of training data to get to the same point or even below. I'm going to finish the presentation of this paper with some qualitative results where you have basically the n-grams, the character n-grams for 2 words that were not in the training set, and you look at the dot product between the character n-grams, and you see that rarity had a high dot product, so red when there is a high dot product, blue when there is a small one, rarity and scarce kind of match, and NES matches ET. So that's quite, I mean, that was fun to look at. It doesn't mean much. The other thing was chip microcircuit, and you see that micro kind of matches with chip, but also circuit kind of matches with it too. And in the middle, this is just junk, so they don't have much similarity. And if you do nearest neighbor queries, so you take these words on the top, and you find the nearest neighbors in your data set using Subword information skipgram, this is our model, or the skipgram model, you see that we get more coherent nearest neighbor queries for words. So that kind of wraps up the technical contribution about word vectors. And after that, we thought that we need to compute these word vectors on many languages. We did that already in the previous paper, but we did that on Wikipedia. And we thought that we need to improve our word vectors, especially for languages which have a small Wikipedia. So in this paper, first of all, we improved our model. And it was kind of an arbitrary choice why we chose the skipgram over SIBO when we did this word vector, like character level information for word vectors. So in this paper, we experimented with SIBO with position weights. So again, this horrible sentence. And here, given the context, we now predict the word. Again, the same softmax. But now, the feature for the context is going to be the sum over all position except the position that you're interested in of a position embedding. So it's a vector that you're going to train. And it's a pointwise product with the embedding of the word. And the embedding of the word is going to be taken as before by taking the sum over character n-grams. So this was a small technical contribution, but it was actually just adapting existing methods to our model. What was most important was working with the training data. So Wikipedia, you can easily consider that it's data of high quality. It's well written, it's it doesn't have much typos, describes a wide variety of stuff. However, it's only abundant for a restricted set of languages. So for English, French, Polish, it's going to be fine, but if you work with Hindi, already with Hindi, it's quite strange that Wikipedia is actually pretty small, and there's a ton of languages which have small Wikipedias. So the idea here was to use Common Crawl. So Common Crawl is a non-profit organization which crawls the web and saves basically whatever it finds on the web. And you can get this crawl data. It's just like web pages that have been crawled and saved. And well, this is the wild web. Like whatever is on the internet ends up in this Common Crawl. So you get a huge amount of data, but it's very noisy. So if you compare in terms of number of tokens, for languages such as German, we had 1.3 billion tokens. For French, 1.1 billion on Wikipedia. But when we mined Common Crawl, we ended up with a data set which contains 60 billion tokens. So it's actually pretty large. For Russian, we moved from below 1 billion to 100 billion. And for languages such as Chinese or Czech, actually, which have small Wikipedias, we ended up with more than 10 billion words. Like when we were working on that, basically the rule of thumb is that 5 billion tokens starts to be a good data set to train word vectors. So here we were really happy about getting this huge data. However, in order to do that, we had to do language identification because crawl data doesn't necessarily come with metadata that says what language is this web page about in. So we had to filter this crawl data by language, and we did that by designing a simple language identifier, which was based on the FastText classification model. And it's basically a linear model based on character engrams. And using this model, we were able to detect 176 languages. And we actually compared this language identifier to langid.py, which is like a standard tool for doing language identification. What we have shown is that we actually have better accuracy with the runtime, which was smaller. That was just like a sidekick from this project, but turned out to be actually a good contribution. And another contribution was adding data because for evaluation. So even if we train word vectors on Hindi, I myself cannot really evaluate if the word vectors in Hindi are correct. So we created word analogy datasets for Polish, French, and Hindi by translating word pairs in the 14 categories which are in this kind of English analogy datasets. So for instance, you would get pairs such as grandfather, grandmother, and you just need to translate that to dziadek, babcia, grand-père, grand-mère, and I cannot read it. And by having that, we can now evaluate word vectors on languages which don't have much resources. So we've seen a big improvement on Hindi, and without this kind of resources, it's hard to say whether or not these word vectors are getting better or not. So in the evaluation we did, we compared to the previous word vectors that were coming from the paper I described before, and we broke down all improvements that I described in the last few minutes. What we show is that on Czech, German, French, Hindi, and Polish, the word analogy improved drastically when we added the crawl data actually to training, with on average almost 15% improvement, and some minor improvements to the model, which were basically tweaking better the hyperparameters of the Subword paper I described before. So this was more of a resources paper. We submitted that to ELREC, which is a conference about resources for natural language processing. So we released the state-of-the-art language identifier, word vectors for 157 languages that were trained on crawl data, 3 new word analogy datasets, and all that is available on the FastText website. So if you ever plan to work with a lot of languages and you need good word vectors, this is the commercial for my word vectors. So all these contributions are part of FastText, which is an open source library that we have, which starts now to have quite a lot of traction, with more than 50,000 people watching the library. A big Facebook user group, so if ever people use this library and have some problems with machine learning related to FastText, you can easily get help from the Facebook group. It was C++ code with absolutely no dependencies, so it compiles, I think it's C++ 11 or 13, so should compile on most modern architectures. It's widely used within Facebook. We worked with, for instance, the search team in Facebook to use it, and it's used by startups and other companies in their products. So now I have an intermission, so you can move around in your seat for a second to kind of do a 1-minute break, and we're going to move basically from natural language processing to computer vision, hence the cat. Okay. So it was a 1-minute break. So we're gonna now move to unsupervised learning for computer vision. And most recent advances in computer vision are based on deep supervised learning. There was a big jump in image classification performance. And this jump in performance was really fueled by having large models and large data. Like, since we had ImageNet, the improvement in terms of classification accuracy, like was getting better and better. And we kind of start to plateau now because it turns out that this huge ImageNet dataset is actually pretty small for some of the architectures. And one of the reasons for the success of ImageNet and these big architectures is the fact that features that you're going to train on ImageNet transfer well. So if you train features on ImageNet, you can use them on downstream tasks such as Pascal VOC or Sun. And part of the reason why is because Pascal VOC and Sun kind of look like a subset of ImageNet. So, however, what do you do if your data distribution is totally different? Imagine now you want to work with medical data or with satellite data. Are features trained on ImageNet in which 50% of the categories are dogs are going to work well on satellite images? I mean, it's not necessarily true. That kind of motivates why people have been looking at what we call self-supervised learning in computer vision. So there was quite a lot of interesting methods that were proposed to learn features. And they rely on the idea of faking up labels. So given data, you're going to try to come up with a heuristic which, given input data, given an image, is going to give you fake labels. And once you have these fake labels, you're kind of back in your comfort zone, supervised learning. Again, you do SGD with these fake labels, and it works. So once you have this feature, like these fake labels, which you came up with a heuristic, you just minimize these kind of cost functions with SGD. So I'm going to just review a few self-supervised methods to make these ideas more concrete. The first one is work by Wang and Gupta in 2015, in which they use object tracking in videos. If you have two videos with object tracks in them, you're going to create now pairs of patches, either coming from the same object track in a video or from two different tracks in two different videos. And you're going to try to learn a function such that patches from the same object track are going to be close together in the feature space, or that patches from different tracks are going to be pushed away. So that's one method. The work of Dersh et al. Consisted in predicting the context. So it was inspired a bit by this idea of skipgram in Word2Vec, but for images where you create pairs of patches, given a central patch, and for instance this patch, you label it with the relative position. In that case, it would be 3. And you just train like a Siamese network that is going to just predict the label 3 for patches that are in a different, like a given geometric configuration. The third method I wanted to talk about is the work of Zhang et al., where given an image, you convert it to LAB color space, you remove the color, you just keep the luminosity, and you train a network such that given grayscale images, it's going to predict color images. So the fake label in that case is just the color. So the main issue with these methods is that they all rely on expert knowledge. You kind of need to have a good feeling of what can we predict given something. You need to define this pseudo label for each new task. And the problem is that if you try to work with NLP, what kind of colorization can I do with that? Like, these methods don't necessarily transfer well. The same holds with speech, even though like relative position may work. You still need to come up with a good idea of how to find the pretext task to solve in speech to be able to train your model. So this is kind of the motivation for our work on unsupervised learning. And our first contribution in that direction was unsupervised learning by predicting noise, a paper that we submitted to ICML, where given a set of images, you generate points on a sphere in a high-dimensional space, and you want to train a function that is going to map images to the hypersphere. And the whole idea about for this paper was about making sure that this function is going to be somehow smooth, that it's going to put hedgehogs together and pizzas together, that there are no like big discontinuities in this function. So the model we proposed was the following. We were learning a function f, which was a convolutional neural network, which was mapping from images to this high-dimensional space. We were sampling points on the hypersphere once and for all, fixing them, and at the same time optimizing the parameters of the CNN and optimizing the assignment between images and these points. So this idea is close to a deep version of what we call discriminative clustering. So what's discriminative clustering? It's a model where if you have n images x1 to xn, you want to learn a function f without using labels. So you kind of write the empirical risk with the loss, but since you don't have a label, you do the minimization with respect to the label also. In our paper, we chose to use the L2 loss, and this kind of looked in matrix form as the minimization of the parameters, of the minimum with respect to the labels, of this kind of discrepancy between the features and the labels. So the whole trick in this paper was to fix the target representations in order to avoid collapse, because if I don't do anything and just optimize over like all binary matrices, you're just going to end up with everyone going in the same class and finding a trivial solution. So we fix the target representation, and we only allow a reassignment of targets and images. So we write Y as the product of a permutation matrix P times C, which is just a matrix that we sample at the beginning, and they are just random vectors on a sphere. So for C, we use the uniformly sampled points on a sphere, and the final objective function for this kind of model is the minimization with respect to network parameters of the minimum with respect to the permutation of this kind of thing. So in terms of optimization, how does it work? We minimize it using a coordinate descent, and we wanted our optimization to look a lot like standard SGD, so it would be done batch by batch. And we do the following. Once you get a batch B, you can compute the feature representation for this batch. You find the optimal permutation for this time step with respect to, by doing optimization with respect to P. It allows you to compute a gradient with respect to network parameters, and you can update your CNN. So the permutation matrix, how can you optimize it? When the network parameters theta are fixed, the problem we have is equivalent to the following thing. It's the maximization with respect to P of this linear thing, because it's a norm that you expand and end up like with two constant terms and only this thing, which is interesting. And this is a linear program on the set of permutation matrices, which is just an assignment problem, and there are efficient algorithms called the Kuhn-Munkres or the Hungarian method to solve that. Because we do it on subsets, on batch by batch, the overall complexity was linear in the number of images. So there was one trick, however, with this method, is that when we provided full images to the method, we ended up with kind of trivial solutions. The network was just learning to push images that have the same color in the same part of the space. So these were the filters that we obtained at the beginning. And if you looked at images that had the same activations, they looked like that, or this thing. So basically like geometrical arrangements of the same kind of color. So we ended up replacing the image by putting a Sobel filter at the beginning. So basically, instead of having the image, having the directional gradients of the image instead. So removing this bias for color. So in our experiments, we trained our network on ImageNet without having labels, of course. We use the AlexNet architecture. And when we do some evaluation, we just basically fine-tune the classifier, which is the end of the network. In terms of baselines, we compared to 3 kinds of baselines. The first one was good old handcrafted features, which was actually the winner of the 2011 ImageNet challenge. Self-supervised methods, the 3 methods that I described at the beginning, and unsupervised models such as the bidirectional GAN of Donahoe et al. So in terms of classification on ImageNet, this is kind of a fake experiment because we trained our network in an unsupervised way on ImageNet and then transferred to ImageNet, which is kind of strange. But what we show is that our method managed to work better than all the other methods. And the improvement over true unsupervised learning, which I consider to be the bidirectional GAN, was almost 4%. And what was strange, not strange, it's like just painful, is that the good old features, which were in some sense unsupervised, are still very far from the performance that we get with the neural network. So if you look at the evolution of performance along epochs, you see that on this experiment, as you roll out the unsupervised training, the gap between the training accuracy is still growing, the test accuracy is kind of plateauing, and there is a big gap between train and test. This may be due to lack of proper regularization, maybe we didn't have enough data back then, or maybe we should use different data. What I didn't say is that this permutation matrix, we didn't update it all the time, we did it only every other epoch. And there were 2 baselines, basically never permuting the matrix, always permuting, and there was a trade-off basically leading to the best performance, which was optimizing every other epoch. And it gave almost 10% over never permuting. So we did a real transfer experiment on Pascal VOC. So Pascal VOC is a data set that contains 20 categories, and we evaluated on image classification, object detection. And what we've seen is that we managed to get state-of-the-art results on classification, and especially our method was working well when only the classifier was fine-tuned, not the whole network. And the method was kind of competitive on the detection challenge. And another observation was that basically the performance of the autoencoder and the GAN was kind of surprisingly low for classification. So just to finish the presentation of this paper, I'm going to show you a few qualitative results. So these are the kind of features that you obtain if you train an AlexNet on Sobel gradients. And this is the kind of filters that we obtained with our method. If you close your eyes, they kind of look the same. We did also some nearest neighbor queries. So if you take these images, you compute features for them and try to find in the dataset images that are going to have the same activations. You get images that really look alike. Here, again, if you close your eyes, it looks similar, but it's an ostrich instead of a dog. Or here you get a pump instead of a kitchen, but, well. So that's about the predicting noise. And following that, we wanted to improve this model for the following reasons. The previous model was relying on the least squares criterion and had a kind of a regression model inside. There was no grouping of images. And the optimization, because we had to optimize this permutation matrix block by block, it was actually quite complicated. So in this paper, the idea was to learn to cluster images. So given a set of images, you want to learn to group images into clusters in such a way that it would be easy to predict the cluster membership by a linear function. By doing that, we have a simple algorithm which kind of looks like EM by updating the clustering and the classification. So the overview is the following. Given an input images and a convnet, you basically pass the images through the convnet. You use them to do some clustering. The cluster assignments become pseudo-labels. And given these pseudo labels and the features, you can do backprop and update the network parameters. So this model was based on two losses. A first one for doing clustering. So our method relies on a clustering algorithm. And in the paper, we experimented with two different kinds of clustering algorithms. The first one, which is, I guess, known to everyone, is k-means. And we also experimented with some more sophisticated clustering, such as peak clustering, which is a graph clustering algorithm. So if we have a CNN, F, and N images, the objective function of k-means can be written as follows. So it's the minimization with respect to the centroids of the average of the minimum with respect to assignments of images to clusters of this discrepancy. And this is basically, this variable is just basically choosing one of the columns of C, which is basically the chosen centroid. And this is the L2 discrepancy between the two. So there was this loss function for clustering, and we had another loss function for classification. And once we had this yi for each image, we could optimize the network parameters by basically minimizing the empirical risk with respect to the network parameters and the linear function w and b, and the discrepancy between this scoring function and the pseudo label. And there are like additional parameters here that we get rid of at the end of optimization. They are reinitialized at each epoch. So as I mentioned before, the noise as target paper had the problem of trivial solutions. And here you have them too. If you don't do anything and set basically your network to predict always the same vector, it can lead to optimal solution to both problems. You can set everyone in the same cluster, and the classifier is just going to classify everyone as the same class. So there were very important details in the algorithm. The first one was avoiding to have empty clusters. So you can modify k-means to make sure that you never have empty clusters by just reassigning one of the points in the dataset to a new cluster randomly. And the second thing was sampling points by class frequency instead of uniformly on the dataset. So you would basically upsample images that are from an infrequent cluster and subsample images that are for a very frequent cluster, so that once you have these two tricks, you kind of get balanced clusters at the end. We trained our model on ImageNet. And ImageNet kind of, we feel that even though it's a very interesting data set, which contains 50% of dogs, it's clustered into 1,000 classes. So there is a natural clustering of the data, which is there, which can bias our method. So we also trained on Yahoo Flickr Creative Commons, which is a data set that was published in 2015 containing images from Flickr with no labels. They just have short descriptions. Sometimes they have hashtags, and plus they are actually Creative Commons 1, I think. It's like it has a license which is quite permissive in terms of reusing the data. And it's bigger. So when we evaluate our clustering, we can compute the normalized mutual information between the clustering and the ImageNet labels. On ImageNet, we can do this control experiment. And the normalized mutual information is the ratio of the mutual information between two clusterings and the entropy of each of the clusterings. And what we show is that along epochs of training, actually our clustering gets better and better and looks more and more like the ImageNet classification. We did other experiments by transferring again to this Pascal VOC dataset. We used the models that we pre-trained, and this time we transferred to 3 tasks on Pascal VOC, which was image classification, object detection, and semantic segmentation. And it's interesting, I think, in practice, because this kind of data regime is what people have in practice. I mean, if you have a startup and try to come up with computer vision solutions to your problems, you're not going to have like 1 million images. So we fine-tune either the full network or just the head of the network. And yeah, I think it's really important for real applications because this low data regime is kind of ubiquitous. So on Pascal VOC, what we've shown is that when we compare to state-of-the-art methods, including ourselves, we have a very big improvement, a significant improvement, which was much bigger than before, both when fine-tuning only the classifier or learning the whole network again. So all this was done with an AlexNet, and we were working with an AlexNet because that's what people were using in the literature, and we wanted to compare fairly. And we also evaluated using a VGG. And when we compared to state-of-the-art VGGs trained with self-supervised methods, what we show is that we managed to reduce the gap with the supervised pre-training from 4.1. I think the previous method was like already closing the gap, but we're getting there. There's still some percents missing, but I mean, this is like an interesting result. We also did some evaluation on a downstream task where you don't fine-tune the parameters because people don't always fine-tune the networks. And on a task which is called instance retrieval, we did that on 2 datasets, the Oxford and INRIA Paris datasets, where there are basically pictures of landmarks. And the task is given an image of a landmark, find the nearest neighbor, and if the nearest neighbor is the same landmark, it's treated as a positive. So there is no fine-tuning here. You just compute your features on the database and then do nearest neighbor queries. And we evaluate that using recall. And what we've shown is that here the gap with the other VGG networks is actually even bigger when no fine-tuning is allowed. So I'm going to finish this presentation with some qualitative results for this paper. Again, nearest neighbor queries. So here is the query. These are the things which are retrieved with a network which had totally Gaussian weights. No optimization at all. You just initialize the network with Gaussian weights. And these are the nearest neighbors you obtain. So they are not perfect. If you close your eyes, they kind of look the same for some of them. And once we iterate our algorithm, it kind of cleans up the clusters, and we end up with things which really look semantically the same. We observed that we basically learned some kind of object-specific neurons by doing deep dream-like visualizations and showing the images that most activated a given neuron. We see that we kind of learn this kind of arcade patterns. This I don't know. These are like feathers of birds and spirals. Yeah, so you can watch these kind of things. I don't think it brings anything to the table in terms of scientific discovery, but there seems to be something happening, and these patterns are clearly not random. So both papers that I presented are open source. We have like open source code for them. The first one was coded in Lua Torch. So I don't know if anyone has coded with that at some point. It doesn't have much users, maybe because of that. The new one is written in PyTorch, and it has a bit more people looking at it. But both have pre-trained models and pre-trained encode for using these networks out there. So if you want to try it out. That kind of brings me to the conclusion of my presentation, and I'm going to start with a short recap. So first I talked about unsupervised learning for natural language processing. How can we train word vectors and obtain good word vectors for languages that don't have much resources? And the solution that we proposed was exploiting character level information and redundancy and sharing of parameters between words. The second thing I talked about was unsupervised learning for computer vision. How can we train CNNs without having any labels? And the models we proposed were based on the idea of discriminative clustering, so grouping points in such a way that it's easy to learn a parametric model to predict these clusters. So everything we've done is always open sourced, and we distribute the pre-trained models for all that for people to work with them. There are a couple of open questions. So this is a kind of machine learning meme, I guess, because Yann Lequin was saying that basically unsupervised learning is the cake and reinforcement learning is just the cherry on top of the cake. It became like it was kind of ridiculous, and it became a meme in the industry. I think that there are important things to do with unsupervised learning. The first one is sentence representations. We managed to get good word vectors, but we still don't have good ways to represent documents. And the recently proposed solutions are kind of not scalable. I think another point is that they are not necessarily trained for all languages. They are usually trained for English, and other languages in which people want to build applications don't have these kind of models ready. The second thing is that for now, models that are proposed for sentence representation are kind of have these scalability problems, such that it's sometimes even hard to fit them in the memory of your GPU if you have a GPU. And I think this is really important to come up with models that can be used by a wide variety of people, including people that don't have very expensive hardware. Another point is the fact that the performance of the models that we proposed for unsupervised training of CNNs is kind of still disappointing. We're bridging the gap with the supervised pre-training, but we're still far. And to jump back on the meme with the cake and the cherry, I think that this kind of clustering, discriminative clustering-based methods really have their role to play in error reinforcement learning scenarios, in which you don't necessarily have an a priori knowledge of what's going to be the environment is going to be looking like. And I think there is a great work to do on cherry cakes. By that, I finish my talk, and I'm ready to take some questions if there are any.